And then welcome everyone to a weekly colloquium of the Physics Institute of the UNAM in Cuernavaca in Mexico. Our guest today is Professor Christopher Stein from the University of Duisburg-Essen in Germany. And let me say some few words on his vita. Christoph Stein studied chemistry at the University of Göttingen in Germany and did his PhD in 2017 at the ETH in the Swiss. He did then a postdoc at the ETH and at the University of California in Berkeley. And since 2021, he's a professor for physics at the University Duisburg-Essen. Dr. Stein's research deals with the theoretical description of physico-chemical processes at interfaces and the development of new models and algorithms for them. In particular, he's interested in understanding how such fundamental phenomena can be used to make energy materials like batteries and catalysts more robust, efficient, and sustainable. So, Christopher, thank you very much for joining us today, at least virtually. And we're looking forward to your talk.
Yeah, thank you very much for this kind introduction. I'm really looking forward and honored to talk in your seminar. And in order to do so, let me check that I set everything up here. Yes, I think you should be able to see my screen now. I will now remove this annoying bar here. Okay, so I will start, and my talk today will be about electrolyte solvation and applied potentials, because that is what basically complicates our modeling of electrocatalytic reactions. And I will let you know why we're interested in this at all and how we want to deal with these challenges. So as Professor Stegmann said, I am a chemist by training and then switched more and more towards physics. So if anything in my language is a bit too chemical, then please let me know and I do my best to explain better. But I think I put some effort in order to introduce all the concepts that we're using, even if they are a bit chemical here. So what we are interested in is in electrocatalysis, as the title said. So one important electrocatalytic reaction would be the CO2 reduction reaction. So you all know we have huge problems with CO2 in the atmosphere, and we would be very happy to convert it into something useful. And if you follow this reaction path here, you don't need to look at all these steps. But what is important here in the end, there is gaseous methane. And of course, methane is a high energy material that can then be burned again as a fuel or so, and is a much more useful material for us than the CO2. So we would like to really capture the CO2 from the atmosphere, drive this reaction, maybe do something even better than methane, like ethane or ethanol even. But anyway, we want to convert it into something we can use as a fuel. If you look at this reaction profiles or relative free reaction energies, you see that there are some uphill steps on an electron volt range here. And this is, of course, problematic because we need to invest energy in order to overcome these steps. And this is kind of hard to do, so it's not thermodynamically favorable. But what we can do is we can use applied bias at this iron surface, so at the electron surface. And what happens then is that all of a sudden, just because of this applied bias, all these steps are downhill, and the reaction will proceed in this way, really forming CO2 from adsorbed on the species, forming CH4 methane from CO2. So the energy that is required here is basically supplied by the applied bias, and often there's not even a change in the reaction mechanism. We just really make this barrier heights of this reaction disappear. If we want to model that, and we need to model that in order to check why some of the materials are not working very well and why and what we can do to improve them, we are facing some problems. So first, we have a reaction that takes place in a macroscopic cell. So we need to somehow consider transport of the reactants, of the products, of the ions that are in this in this system here, and this is very slow. The transport here is on a completely different time scale than something else that is interesting to us. And that other thing that is very interesting are the electron transfer reactions that really happen here at the electrodes. So these happen extremely fast compared to the transport here. This is challenging for simulation, even if we just look at one of these two processes. So in my talk, I will not even touch the first point, but this here is already problematic enough because we have an electronic structure here under applied bias. That is not what we usually do in DFT. There we have basically just a fixed system. We need to somehow deal with the electrolyte solvent. So here it's nicely drawn that you just see like whatever you put in the CO2 and all of these mixtures that you get out. But of course, this does not happen in air. This happens under some solvent and also includes electrolyte ions so that really the charge flow can happen here at all. And this is challenging for our electronic structure methods. And something that is also very important is the heterogeneous structure of the electrode. That's one of the newer research topics we are interested in, but not part of the talk today. But you see, there are already quite some challenges for the simulation, and we need to be quite accurate in order to really make predictions and rate if a material is valuable for the reaction we want to drive or not. Additionally, we see, and you can see this already here in this sketch, we have many competing reactions, and ideally we would change the catalyst structure somehow in a way that we just get our preferred material or preferred molecule. Maybe here this ethanol is one of the things people are most interested in. What do people do to model this, these reactions? There are basically two big schools or two big approaches that people use. The first one is called the computational hydrogen electrode. And there you just use a simple step. So for every step that I showed in the first slide, where you saw this initial, where you also saw the steps that then eventually went down, we just assume that we can write them as an addition or removal of a proton and an electron. So for example, we have the CO2 adsorbed on the surface. We do this addition step in this case, and then we have COOH adsorbed on the surface. So the star always means that it's adsorbed on the surface and not floating around in the gas phase. Where does this come from? In reality, this proton and the electron comes from the other half cell. Yeah. So in order to close the circuit, we do not explicitly calculate it. We usually are just interested, or we just only able to calculate in one half cell. And we have some kind of a reservoir assumption here that it's just supplied with a certain chemical potential. And then the free energy of such a reaction step here is given by this. So we have the free energy of the absorbed product minus the free energy of the absorbed reactant, and these two ingredients that we also need in order to promote this reaction. This here we can easily calculate. So what we would do is just think of a structure where this is absorbed on the surface and run a DFT calculation and get the energy. And then with some approximations, we can also get a guess of the entropy. The same here. However, this here is not immediately clear how we get this, but there Norskov and Ross Meisel had a fantastic idea that is very simple and therefore very, very widely used. And they just identified these terms as half of the formation energy of H2. And you can calculate this with the same computational method that you use for this calculation. So you have like an internal computational standard, which is the same what you would do in the experiment, because you also there have an internal standard by some reference electrode, for example. And you can also add a bias potential here, just as an external contribution that you add here. So just E times whatever bias potential you have. But that means that the bias is not explicit in the calculation. So we just add it later as a correction term here, but it does not change in a self-consistent way the electronic structure that we have here, for example. So it's basically something that allows us to perform this calculation, but more like a trick, and a trick that works extremely well in many cases. Another approach would be grand canonical DFT. So we allow our system to be grand canonical in the number of electrons. So we do not have a set number of electrons, but due to the applied bias to the hooking up to the battery by principle, we allow electrons to flow in and out of the system. So we now have a constant chemical potential, and that means that each orbital can now be fractionally occupied. It's also something we need to be aware of in our methods, because usually we have either an electron in an orbital or not, but not something like half an electron. What is half an electron, right? So we must be aware that this needs somehow be dealt with. And what you do then is you minimize now the grand potential, where you have the free energy, and here you include solvation already. So basically, this is a bit implicit here. You have a fixed chemical potential, and you have here the total number of electrons. And now you just say that you control the orbital occupation by this temperature term, and you just assume a Fermi type occupation here for each orbital. So here you have the orbital energies, some a fixed chemical potential, and then depending on the temperature, it's either fully occupied if it's like a very low temperature, and at high temperatures, of course, only fractionally occupied. You can include bias also by adding it to the chemical potential. For example, a chemical potential for the standard hydrogen electrode is another standard that we can also add in our computations. And then we simply adjust the electron number here so that we can minimize this grand potential here. So we just change this number of electrons, and therefore also the distribution here to minimize this grand potential. This is usually done numerically by direct minimization. And another similar approach here would be that we relate the bias potential to the Fermi energy of the system, and there also we adjust the number of electrons so that the resulting Fermi energy that we get from our calculation corresponds to this applied bias potential. So basically that this equation is fulfilled. So we can, by changing the electron number, we will change mostly this term here, and we do this until we get the bias potential that is the one that is used in the reaction. This here is usually not done in the direct minimization. It's a nested loose self-consistent field where you can then include also electrolyte solvation, and you optimize for the orbitals and the electron number in two nest cubes. When people do this, we see here for one reaction, but different reaction steps. The left bar is always for this computational hydrogen electrode, here just termed DFT, and on the right-hand side, or the right bar, is always the grand canonical version. And you see that the results are more or less very, very similar. So these very different approaches give very consistent results, and that is why I said at the beginning that this computational hydrogen electrode approach that is so conceptually simple is very, very successful and applied a lot. However, there are limitations. We always have to assume a simultaneous proton-electron transfer step. There might be reactions where it's just not possible because this is not what we're interested in. Maybe we're not really interested in reactions involving protons. The Fermi occupation might be unrealistic. One problem, for example, is what is this temperature that we set there? That is hard to determine for us. It's certainly not the temperature around us, or the temperature with the outside temperature where the reactions take place. And most importantly, all of these methods require periodic density functional theory calculations. And we know that most of the activity of catalytic reactions does not take place on a perfect single crystal surface, but rather at all the defects that we might have or that arise if you have a certain temperature. There might be steps that form on this surface and so on. These are really the reactive sites, and we cannot easily model them with periodic boundary conditions. So there is room for some other method where we can use nanoclusters or defected sites in order to model these electrocatalytic reactions. And there we cannot use these two otherwise quite successful approaches. If we think of biased systems, you might, and I think Professor Stegmann specifically, might think of molecular junctions immediately. So if we compare these two, we have here the electrocatalytic cell, and here like a sketch of a molecular junction. What we do here, we use an applied bias to supply energy for a reaction. And here we use an applied bias to send a current through a molecule, for example, where we have these two electrode kind of tips. Here we actually do not model the full circuit, so we do not model the full transport. What we usually do is we just look at one electrode, be it the anode or the cathode, and we couple this somehow to an electron and potentially a proton reservoir, and then we look what happens at this coupled electrode, for example, reactions that turn reactants into products. What if we do something very similar here? So if we do not model the full circuit, but we just model part of the system, but otherwise use a very similar approach. Yeah? So this is, you will later see, this is more of a historical way how we thought about modeling this. Yeah? So in the end, we do nothing that is non-equilibrium dynamics or nothing that is electron transport. It's just a bit how we came up with our new approach. This is an equation to calculate first the non-equilibrium density matrix for such a molecular junction. And I do not want to go into too much of the detail here. We have a left side here and the right side here. This density matrix somehow formulated, for example, in an orbital basis. So it's a reduced density matrix here. We have self-energy terms and Green's functions. But we see here, this is describing the non-equilibrium electron transport because of this term here. Yeah? We have a difference in the chemical potential between the left and the right side, and this is basically what allows us to send a current through this here. But what we wanted to do is simplify the system and just look at the left-hand side. And then all of these terms that depend on the right-hand side, we can just cross out. Actually, that is something that comes out. You can derive this, but in the end, what it boils down to is you can just ignore all the terms that have an index R that somehow refers to the right-hand side. So of course, we do not have any electron transport because there's nowhere to transport to, and we don't have the self-energies here for the right-hand side. So this is now an an expression for the reduced density matrix of such a system. And we see here we have an upper integration limit of this energy integral here that we can identify with the chemical potential, and we can modify it and therefore simulating some bias potential. So the higher that integration, that upper integration limit here is, the more electrons we let in our system. Okay. This is how it looks like. To look here, this is notationally from -infinity, but numerically it's enough if we put this to the lowest orbital, so the lowest energy eigenstate of our system. This here can be the chemical potential and the bias, and we have an integral over the energy here. This GR is a retarded Green's function constructed from an overlap matrix, the Fock matrix in our case, and a self-energy matrix. And here we start with a very, very simple approximation. We say that our energy, a self-energy matrix, is just diagonal and consists of two parameters. One is just an energy shift, and then here we have a complex part, imaginary part, which is basically a broadening or a leakage. And depending on if we have this or if it's zero or not, we allow electrons to flow in and out of the system. So the larger that value, the basically easier it is for electrons to flow into the system. And the upper integration limit is the chemical potential of the reservoir, potentially changed by the bias potential U here. Numerically, you can solve this integral over the complex contour, but if the self-energy here is parameterized like this and energy independent, then you can derive an analytic expression for this, which is of course nice for us because it's just usually faster. Faster to calculate. And these X and Y here are the solution of the following eigenvalue equation here. So we basically, with all these approximations, especially approximations here, we arrive at an expression for the density matrix that we can then use in a self-consistent way to optimize when we set these parameters, so the chemical potential, and of course, assume some values for these parameters here. And if we can compare to experiment or to other calculations, we might be able to optimize this here and arrive at a very simple expression for such a system without having to impose anything on the structure. So here we can really use nano clusters of any type and any geometry. So we have a grand canonical model suitable for nanoclusters and can include the bias potential. So we are halfway there, but we need to solve the equations, and that is in quantum chemistry what we do all the time. We start from some density matrix, we update the Fock matrix. In this case now we update this retarded Green's function because the Fock matrix enters here, and from this then with this integral that I showed you before, and now this analytic equation here, we can update the density matrix, and then we just do this until we converge for a fixed energy shift and a fixed broadening. This dice here, this is a typical ICF acceleration that basically includes some information on previous steps. So you have kind of a memory effect that helps you often that you don't have like oscillating behavior in the solving of this problem. So how does it look like? We wanted to look at a very simple model system. So we have a chain basically of 6 hydrogen atoms here, all equidistant. And we do use a minimal basis. So we only have 6 S-type orbitals here and do a Hartree-Fock calculation. We do not for now apply an energy shift, but we of course need some broadening in order to see if electrons are really flowing in and out of the system. This is what we get. We get 1, 2, 3 occupied orbitals because each of the 6 orbitals can be doubly occupied, and 3 unoccupied orbitals. The reason here that I call them occupied is that at 0 leakage, we would have, of course, just doubly occupied. Yeah? So that would be the case where we do not let any electrons flow in and out of the system, and you would fall back to our normal Hartree-Fock or later DFT description. That is then non-canonical. So we have an independent variable, the chemical potential mu, so the upper integration limit, and we have dependent variables that are the energies of the orbitals and the occupation numbers of the orbitals. And if we look here, we see, so this here is the lowest energy orbital. You see here its shadow. And we have an occupation of 2, yeah? So it's so low in energy that although it's basically allowed to exchange electrons with the system, this is so low in energy that this will be the orbital that is almost always filled with electrons. On the other end, the highest energy orbital here is almost always empty. Only at really large chemical potentials we see that there's a little bit of occupation. And of course, in the region between the highest, or in the non-coupled case, highest occupied molecular orbital and the lowest unoccupied molecular orbital, there we really see a change in the occupation number. And this change depends on the value for the chemical potential that we use. So if we use a chemical potential that is rather low, then we arrive at a situation where we have 2 and approximately 2, but here only 1.7 orbitals. So we have electrons, sorry. So we have less than the 6 electrons we would expect for this uncoupled case. On the other hand, if we go to very high chemical potential, we see that if we sum up the occupation numbers here, we arrive at more than 6 electrons here. That's mostly because this usually unoccupied, lowest lying unoccupied orbital here still has some occupation. So we're really able here in this model system to see that we can let the electrons flow in and out of the system and therefore emulate the effect of an applied bias potential. We ran into some problems with the SCF convergence because we have an additional degree of freedom, the orbital occupation numbers. And so, convergence problems are maybe to be expected. But what would be a better idea here would be to do a direct minimization with an orthogonality constraint, because our orbitals, that is our requirement, still have to be orthogonal to each other. Yeah? And there are methods that do this, but there are no methods that do this for occupation numbers that are non-integer. So this exists, but what is different in our case here, if you think about what we want to do here, we want to we can think of an analogy. So if you want to find a 3-dimensional vector that is able to minimize whatever function it depends on, but we have the constraint that r dot r is 1. That is the definition of a sphere. So we arrive at a curved space here. So our solution for the orbitals, if we have this orthogonality constraint, is something that we need to search on a curved space. And this changes the approach we can use quite dramatically. If we have only occupied and unoccupied, we have subspace invariance, and we can minimize the energy just by appropriate occupied virtual orbital rotation. So this is a subspace optimization on the Grassmann manifold. If we have a curved space, then all orbitals are fractionally occupied. We have no subspace optimization anymore because we don't have a definition of these subspaces occupied and virtual anymore. Yeah, so all orbitals are partially occupied, and this corresponds to an optimization on the Stiefel manifold. This is something you can still do. You could either think of, if you are in a curved space, you just take a step in a gradient direction to minimize the energy. That's still the goal, right? And of course, then if you just take the step in the gradient direction, after you took the step, the orthogonality constraints are violated. So what you could in principle do is just take the step and then re-orthogonalize. But the more elegant approach would be to take a step in the direction of the geodesic, so the shortest path in between 2 points in this curved space. And this you can do by applying this approach, where you first calculate the Lagrangians or determine the gradient of the Lagrangian. So you determine the direction you actually want to go, and then you project the gradient to the tangent space. Then you're here, and what you can then do is calculate the geodesic as the matrix exponential from this projected gradient. And with this approach, so if you do these 3 steps, you can always guarantee that you end up still following these constraints. Yeah? So you're still on this orthogonality constraint by following the geodesic here. And if we have this approach, then we can just define normal steepest descent or better conjugate gradient algorithms but now that guarantee that we don't have oscillations in our SCF procedure, but allow us really to find the minimum in the orbital space. I will go through this really quickly. So in the Lagrangian, we have, of course, the energy and also the orthogonality constraint. We can write this for a column vector of C. And there's the problem that basically we need to take into account these occupation numbers here. So if you want to define this gradient, this is somehow a function of the occupation numbers. If the occupation numbers are constant, this is not a problem, but in our case, the occupation numbers were derived from this equation that I showed you before. So they are part of an eigenvalue equation. And if you want to include this then in a kind of chain rule and have this as a term in the gradient, you can do this, but it's not so easy to do, because these terms here, they are like the results of an imaginary or a complex eigenvalue equation. And yeah, it's doable, and we're looking into this now, but for now we just came up with a more pragmatic solution. So we do an initial phase with the SCF approach so that we're close to the solution. And then we do an inner and outer loop. So we do the orbital optimization for a fixed occupation number so that we can just use this gradient formulation as it is here without any chain rule. And then we do an outer loop where we extrapolate the occupation numbers again based on the previous steps. And with this inner outer loop, we are so far able to converge all of the calculations we were interested in. But it's not very elegant. Ideally, we would like to have the real gradient here that includes also the gradient of the occupation numbers from this eigenvalue equation. But apart from this technical detail, we can look at how our model is performing. And for this, we did a simple test case. We looked at hydrogen rings, and we want to perturb this hydrogen ring. So we just had a charge that we slowly moved towards that hydrogen ring and got this potential energy curve here. Yeah? This is a ring with, I think I showed here 40 atoms, but later we went to something that is converged in the sense that it really behaves like a quasi one-dimensional periodic system. And that was like, we reached this 200 hydrogen atoms, I think. But this is the typical curve you get. So you have a preferred distance here. And we want to see if with our model, just the same model I showed you before, for some reason a different distance here, if we can emulate this behavior. Yeah? So maybe we can find parameters, the only 2 parameters in our model here, that reproduce this curve. Yeah? So that we have really a model that allows us to get some properties of this large periodic system from just a system with 6 atoms. In order to do this, we just try to scan this parameter space of epsilon and eta. And what we wanted to do is to reproduce this energy gap between the lowest point and the point where the charge is really, really far away. We just do it by a 2D scan, and then we find the values with some optimization method. And then we want to see, okay, if we have this optimal position here, or the optimal values for epsilon and eta, will we be able to produce all the other points that are in between here? So is there some transferability of the model, or will we just be able to be make predictions in a very, very constrained space. This is what we did, and this is also where this part of the research is standing right now. So we did this parameter scan here. The brighter the area, the better the approximation. So the smaller the error with respect to this energy gap. And for 3 regions, 1, 2, and 3, we were able to be very, very close to the correct potential energy gap here, or to the dissociation energy, you could call this here. And after reoptimization, you see that we have fixed the end of this value here. So at large distances, and you see all of these values here are on point. But only one of these 3 sets allows us to give good transferability. So this dark blue curve here, this is the original data. And you see that the green curve here, so this set 3, that are the parameters here, where we change the orbital energies artificially a lot and only have very little leakage. So we only allow the electrons to fluctuate a bit here. That allows us to be close to the system, to the original system. But so far, we're quite hopeful that we can use this method, because right now what we did is only using 2 parameters. We can, of course, make it more complicated. We can make the parameters orbital dependent. We can just get rid of this diagonal assumption that we did from the start. And since already with this here, we were able to reproduce properties of the system, we hope that we can extend this in the future. With this, I think I would like to go to the second part of my talk, because so far I only talked about the cluster part, the ability or the hope that we, or the need to have a method that allows us to get rid of the periodicity of the system, so that we also are able to model defects. But another thing that we need to take care of is the electrolyte solvation. So we don't just do this in water or whatever, or ideally the gas phase, but we have electrolytes here. And historically, there have been, of course, many formulations of solvation models, starting maybe with Helmholtz here, who applied just fixed countercharge at a given position D. Then Dewey and Chapman, who at the charged surface and said, okay, then we have a diffused layer of these ions, and these ions are somehow hydrated. So there's a kind of fixed sphere of waters around it. And then here it's like in a Boltzmann distribution, goes away, diffuses away from the surface. And that was then modified by Stein in 1924, so almost 100 years ago, where he said, okay, this seems to be up to today, the very good approximation to say you have a first layer that is kind of rigid of ions that are close to the surface, still with the hydration layer, and only then you have this Dewey-Chapman type diffuse layer also at the outer bounds. And of course, if you want to model this, you could say, okay, I just take all the water molecules, I take electrolyte molecules, but this is expensive. If you want to do it explicitly for routine applications, you cannot do this. Maybe if you really just want to prove a point, or want to to benchmark other methods, you can do it, but not routinely. But all other approaches, so that would be implicit electrolyte solvation models, is still based on these ideas. So all we want to do is mimic something like this at the electrode surface. And this looks like, or can look like this. So we start from the Poisson equation in vacuum. I guess you all know that very well. So we see how we need to modify this for our purposes. And the first thing we do is we introduce a position-dependent dielectric permittivity. So that closer to the surface, it can be different than further away from the surface, just because there are concentration dependencies of this. This is a generalized Poisson equation, but this does not have ions yet, so we need to introduce them. We introduce the charge density of these ions that are flowing around in the system, and we do this in a very simple way. We say that each ion has a charge, of course, and there is a concentration of these ions in our solution, and this concentration now should be a function of this phi here that we solve for in the end. So you see, in the end, we have again an iterative cycle that we want to solve. We do this on a 3D grid with a multi-grid solver, and we can do several approximations for this concentration here. we can just use this exponential term. So that would be a Boltzmann distribution that we assume here. So it's of course still modulated by the field, but then tailed out by the temperature. So the higher the temperature, the longer the tail of where we could still find ions away from the charged surface. And this lambda here is something I will tell you later, but this is Stern thickness. So how this rigid layer that or it's supposed to mimic the rigid layer that we talked about on the slide before. If you have an exponential term, you can linearize it, and this is done frequently. And in one of the most popular programs, this is like the standard. And what you can also do is you can say, okay, in this approximation here, the ions are still point-like, so they can come as close as they want, but this is of course not very physical. We can introduce some excluded volumes, and with these excluded volumes, then we arrive at an expression that looks like this. That should be physically more accurate, but in practice, we are really lucky with error compensation here. So this actually the standard model gives better results than these poor results of the size-modified Boltzmann equation. But this will certainly change in the future when we improve the model in other regards, and this error compensation will not hold anymore. Okay, so we have two functions that I did not introduce. First, what is the function of how does the dielectric permittivity change? And there we just use an error function expression, and we have an ion exclusion function where we say, okay, the ions, they are separated from the solute by the hydration shell, so they cannot come as close as the water, for example, to the solute or to the electrode surface. And we can also visualize this. You see here, we have inside the molecule or inside the surface, we have like vacuum permittivity for the solvent, and then it ramps up to the solvent value. So this is water in this case, and then only after some time, we have also the ions because they are separated by their first water layer. So this is basically here, this separation by the ions join a bit later or have larger distance from the surface. Maybe no details here. This is what it looks like. So if you have a molecule, now not a surface here, this is what we get from the dielectric permittivity. You see it's a bit closer than the electrolytes. That's already to be expected. But what we see now as a result is that we can define a polarization charge density, and this is something that you would get from any solvent model anyway. So you have like this very thin shell here where you have a charge density is just from polarization, from the interaction of the molecule with the water. What is more interesting, because we're interested in the electrolytes here, is how after we solve these equations, how does the distribution of the mobile ions look like? And you can see here, they cannot come as close as the water again, but then you see there's a clear separation. We have here a negatively charged part of the molecule. So the positive ions will accumulate here and the other way around, of course. And you see here, the tailing out is kind of slow, and that the higher the temperature, the slower. So we need larger simulation boxes here, because here you can really use the absolute minimum box, basically. Maybe I want to talk for a few minutes about how we try to get the parameters of this model right, fix the parameters of this model. So if you look here, we have this a parameter that gives the distance of the ions from the water, and therefore for the molecule. And this is something we need to fix. There are experiments that describe a linear relation between the free energy of solvation and the ion concentration. You can hear, and this is what we call the Sechenov coefficient. And if we change the proximity of the ions to the surface, we will change, so this is the Stern layer thickness, this will affect the Sechenov coefficient, so the slope of this relation here, and therefore this coefficient. And we can compare to experimental data and then use that to fix the only parameter in our model, which is the Stern layer thickness. First, I told you before that the size modified Poisson-Boltzmann does not behave very well, and you see that here. So we expect experimentally this linear relationship, and that works perfectly fine for the Poisson-Boltzmann case. But for the size modified, we see this deviation. This has been seen by many people, and for some reason not explained that honestly, I think, because it's not that very important. So most people just go with this simpler approximation for now. There are so many approximations here that that it's just fine as long as you get the general trend. Yes. What we then did in order to fix the parameters, and there's only one reason I want to mention this, is that we are here in a low data regime. So this is really not a lot of data. And we have experimental data that ranges from the 1920s to basically 3 years ago. And we cannot trust all the experimental data. So the least we can do in order to verify what we are doing is some outlier detection to see if there's any reason to believe that some of this data is not very trustworthy. And we just, since we know, we can assume or should assume here between the calculated addition of coefficients and the experimental ones a linear relationship by in some way with some slope. We can do ordinary least squares, but we should really something that tells us if we have outliers, and this Ransack method helps us. So basically what you do, you exclude some of the data points, and if this has a huge effect on the outcome, then you would think maybe this is an outlier, and then there are some other checks that it does, so that we can exclude this most likely bad experimental data. We were able to define an optimal Stern layer thickness with this, and now get really good agreement with the experimental results. But how good is that? And in order to really understand how good these implicit models are, we teamed up with experimentalists and looked at a very specific example in a joint theoretical and experimental work. And the experimental collaborators, they were able to do terahertz spectroscopy on a gold surface at very low bias potentials. Now, these experiments, you need to hope that you do them right, because you get like beam time once a year, and then you either have good data or not. So this is why this project took, I think, 2 years to finish, because we needed to remeasure some data. But what we were able to do, or our colleagues were able to do, is to identify a loss of an hydration shell. So all these water bands here are very specific. It's like a fingerprint. And if you then change the bias potential here, at some point, of course, if you make this negative, this force, the electrostatic force here will be so strong that you will get rid of this hydration layer and be directly here. And this you can measure the absence of these waters here. You can measure with terahertz spectroscopy. And what we found was something that surprised us a bit, and that is not captured by the implicit solvation models, because we saw if you apply a negative bias potential and have a negative charge here, then sodium loses its hydration shell already at low surface charges, so quite early in the experiment, whereas chloride, even for high surface charges, keeps the hydration shell, or at least medium surface charges. Eventually, of course, you will lose the hydration shell. And we were wondering, why is there this asymmetry effect? And for this, we did quantum chemical and molecular dynamics calculations. The classical molecular dynamics simulations were really important here mostly for one reason, but that has been seen by people before, that on some metal surfaces, the water tends to form this two-dimensional layer here. So you have the electrode, and then really just the 2D layer of waters where all the hydrogen bonds, all the interaction is just within this layer here, and not with the bulk. So you really have a hydrophobic interface here between the first water layer and the bulk water. On the other hand, we did quantum chemistry calculations to investigate the microsolvation, which basically means we wanted to know if the ion is completely free and there's only a cluster of waters around, what structures does it prefer? So how does it prefer to be bonded by water? And we see that, or saw that, chloride really prefers this asymmetric hydration environment. So basically, part of it's more like a surface situation here. So part of it is completely not bound to water. And sodium always wants to keep this symmetric hydration shell. And we then postulated and confirmed with more ab initio molecular dynamics simulations, for example, that you can then that sodium likes to bind here easily, because you have to pay the price. So once the sodium is here, it so much wants to be bonded to water that you already pay the price at this position of breaking this hydrogen bond network. And then in the next step, the two waters are just replaced by two of the negatively, now because of the bias potential, negatively charged metal atoms. So the price is just paid. The price you have to pay is just already paid earlier. And chloride is perfectly happy here because it has this preferred solvation environment. This is, of course, just an enthalpic point of view. So there's no entropy consideration really here. And we're adding this, but we're seeing that in the cases we looked at these low bias potentials, the enthalpic argument seems to hold also in other cases for larger ions, smaller ions like lithium, for example, and also other surfaces. What are we doing at the moment? We still want, in the first part of my talk, I talked about these these cluster models here, where so far I only talked about the hydrogen chains, but of course, in the end, we want to model a metal cluster here where we can really do reactions. In order to do this, we need some automated parameter optimizations for these self-energy terms that we really just treat as free parameters here. And we need to do this for larger systems. Ideally, we would have an analytical gradient for the occupation numbers so that we do not need this nested loop procedure. And of course, there needs to be some testing. So these hydrogen chain tests are really the first thing we did there. Then we want to somehow include, or we are basically doing this already, the asymmetry that I showed you on the previous slide between the positively and negatively charged ions in the implicit solvation model. So it's not too difficult to understand. It's the interaction of the dipole with the dipole of water is of course asymmetric, and this leads to the different solvation of positively or negatively charged ions, even if the size is the same. And what we always, of course, need in order to run massive calculations is we need to be more efficient in our implementation, and also their analytical gradients would, of course, greatly help, so that finally we can combine the two models and really model chemical reaction on a nanocluster in this electrolyte solvation model. I think I have like 10 more minutes or so, so I want to briefly introduce one more topic we worked on and that we now recently published. And just to put it into context, when I started about 10 years ago and did my first research, what we were, for example, interested in is like the bending potentials of these molecules. And the reason for this is that they are interstellar molecules. So with like radio astronomy, you can detect their vibrational and rotational spectra, and you can do this with really, really high precision. So we did like the most expensive quantum chemical or electronic structure calculations you could do at this time to, for example, calculate the bending potential of 3 to 4 atomic molecules. So it's really 3 and 4 atomic molecules. You could do larger things already at this time and maybe even 50 years ago, but certainly nothing like this. This is something that came out a month ago. And this is a simulation of such an, not electrocatalytic reaction, but a heterogeneous reaction. And this is a simulation where every atom is treated as an atom. There's no approximations, no coarse graining. It's really an atomic simulation with 1 billion atoms. And although, of course, this is more personal, not a fair comparison, there must be something that happened in this time, because 10 years ago, something like this was absolutely unthinkable, that you could do this at really ab initio electronic structure level. And what that was is, of course, already said in the title. We can now, with neural network potentials, really take a lot of the load of the electronic structure calculations by training neural networks and using them to run our simulations. And this is something we were interested in, and we did recently. As a motivation, some of us were interested in this hydrogen combustion reaction. So it's all possible ways to form water, just starting from H2 and O2. You can formulate like 19 reactions. And that was the main reason why this was interesting for us, because it was still in a range that is manageable. So 19 reactions is a data set that you can handle, something you can overlook. And it's a good first example for a newly developed reactive neural network. We calculated structures of this system with DFT, with like the highest we could afford for all of these calculations. We did intrinsic reaction coordinates, so like the minimum energy path connecting the reactant to the product for all of these 19 reactions. We did ab initio molecular dynamics to really explore more of the space around this minimum energy path. We also did normal mode displacement. So for each structure, we just let the molecules vibrate to generate even more structure to get really a good idea of the potential energy surface. In the end, we had like 300,000 energies and 1.3 million force vectors. So quite sizable data set, but not really like big data. So it's something where we really still need an efficient model. And this is how it looks like for one of the reactions. So you start with some reactant. This is in terms of coordination numbers here for the two hydrogen molecules. So they are bonded here. So you would expect a 1. In the product, the OH is bonded. So the other coordination number should be at 1, and somewhere in between is the transition state for this reaction. So the reaction with the minimum energy path goes from O plus H2 over the transition state here. And you see all these other data points here are calculated either by ab initio MD or by these normal mode displacements. And we did this for all of these 19 reactions. Why is it challenging? Because we have chemical bond breaking. So if you go back here, from here to here, that's a kind of small part in space, or it's a fast reaction, and really on this intrinsic quality reaction coordinate is kind of short basically, but we have a huge change in the energy here. So what the network sees is just the structure, and the structure changes a little bit and you get already a very different energy. So that is kind of challenging. And also the generation of accurate data is quite costly. So here this was manageable, but still it took several weeks to calculate all these data points. So we need a model that is not that data hungry, and something that gives us high accuracy so that we can really capture these bond breaking processes. And our solution is we termed Newton net, and the key, so I cannot go into all the details, but the key really to achieve this here, the high accuracy and the less data hungry model, was that you need a mixed invariant and equivariant model, because if you think of the energy, if you rotate the system, of course you want it to be energy invariant, but the forces, if you rotate this whole thing, the forces need to rotate with your rotation, right? Because if there's a force between these two atoms here and you change the whole thing, it cannot be that the forces stay in the direction where they are. They should still point towards each other. And we did this in the architecture, encoded this in the architecture of the neural network by applying Newton's third law. So we have this message passing protocol that is then multiplied by the derivative of these two positions here. And by this, we always agree by applying the same message with the different derivatives here, either for IK or KI, we always have the actio-reactio captured, and we have all the equivariance of the forces guaranteed. This is how it looks like for a given reaction. So you see here the green and the blue, or for a given data point, you see the green and the blue arrows. These are the forces, and you see at the first layer of this neural network, they don't align at all. Yeah? The first guess of the model is not very good. When you go to the second layer, it's already better, and already at the third layer, they align perfectly. And it's important to note that more important than the length of the vector, that we can tolerate some error, the direction is absolutely important for the molecular dynamic simulations that we want to do. These are the learning curves. So the horizontal lines are our competitor at the time, and we can, with less data, be much more accurate. So you see here for the energy, already with like 500 data points, we're better than their value at 5,000. But this is an extremely fast developing field. So already last week, there came out a new model that beat us then again. Yeah? But it's also important you do not need to really go at zero here. You need to reach something like chemical accuracy. So if you're at this region here, that is already considered very good. Yeah? And I don't think it makes much sense to compete there, because there are so many groups working on this to order. If you want to do the best model, that will be a tough race. The good thing, or something that we want to look at now and that we can now do, is to employ an active learning strategy that helps us to reduce the data even more. So if you think of this reaction and the intrinsic reaction coordinate, we just see that part of the configurational space that is important to describe the reaction. So really just leading us from the products, from the reactants to the products. And we can map this configuration space, this part of the configuration space, to a principal component space defined by this intrinsic reaction coordinate. And this can look like this. So we reduce the dimension from a formerly 9-dimensional space to a 2-dimensional space. And in this 2-dimensional space, all the important parts happen. So it's a dimensionality reduction, where then later we are able to add all the other data in this new coordinate system. And the nice thing here is that this we can do the other way around. So we can also generate data in this space. And this, since we know that this space is the chemically meaningful space, if we only generate data points here, we capture the chemically meaningful parts, and we can just make sure that we generate all these data points that we need in order to train our models, and thereby reduce really the randomly generated data we would do with ab initio molecular dynamic simulations in the initial case. So active learning is possible. With this, I'm at the end of my talk. I want to thank my group for doing most of the work here, especially Mohammed, who works on the solvation models, and these are the active learning. Some other stuff has been done before I started here. I thank you very much for your attention, and everyone who worked with me, and the funding, of course. Thank you very much.
Yeah, Christopher, thank you very much for this wonderful, very interesting talk. Lots of very interesting work. Are there comments, questions from the audience? Well, I may start. I have several questions. So yeah, the first one, I understood that you excluded somehow the drain, that you, in this analogy between molecular electronics and modeling and electrolytic reactions, catalytic reactions, what is the advantage of excluding the drain? This I did not get.
Okay, yeah. I mean, it was more, if we think of this system here, yeah, so the reaction takes place at the electrode, and then the charge transport takes a long way and at a completely different time scale. Yeah, so we do not have directly the other electrode here. So, but we have to transport the charge through the liquid. So I was not sure if I should present it this way, because we just use the same notation, but we don't do any what we more do is we have a cluster coupled to a reservoir, and we just use the same description as people use in molecular junction.
Enjoyed and appreciate this analogy, because I know very well this stuff from molecular electronics. So I understand that the important reaction takes place at the electrode interface, and then in between you have much space which isn't that interesting. So
exactly.
Okay.
You really look at the elementary reaction steps, not at the transport.
I see. Okay, and well, you have this analytic expression for P. I don't really get where in P enters then the U, the potential or the bias.
This it would enter here. Then you would have a mu plus U.
I see. Yeah. But then I have computationally, you have to calculate the eigenvalues for this analytical expression.
Yes, we have to calculate the eigenvalues of the Fock matrix with the self-energy.
I see.
Which is for us not a big problem, because in the if we just do a normal SCF, we do have to solve the eigenvalue equation just for the F, right?
I
So in
see, I
Hartree-Fock,
see.
you would just solve in your basis the Fock operator then, and here we just have this additional only diagonal term, so that does not add anything to the overall cost.
But you not only need the eigenvalues, you need also the eigenfunctions, right?
In principle, yes, yeah. So this B here are the eigenvectors, the eigenfunctions,
Yeah,
and they enter here
yeah.
again. Yeah. So if there would be no coupling, so if the temperature would be 0, or here the broadening would be, or if the whole self-energy would be 0, then we would just have fall back to normal Hartree-Fock. Now there's just the density matrix is then constructed by the eigenfunctions. So C, we would usually call it CT, multiplied by the occupation numbers that then only are non-zero for the occupied orbitals.
I see. The analytic expression comes from contour integration, right? In the complex plane.
Yes, in principle, yes, yeah. So we also have this implemented the numerical integral because we're integration because we're not sure if you can always get away with the diagonal approximation, and more importantly that this is energy independent. Yeah? We integrate over the energy and assume this to be just fixed parameters. And
I understand, but the problem is with low eta you have very sharp resonances in this integral. And
yes, exactly,
to perform
exactly.
it, this is computationally harder than solving all the
exactly
the eigenvalue problem. I see. Okay. Are there questions from the audience until I continue with my own ones? Yeah. If not, yeah, I did not really get, you compared this chain of 6 hydrogen atoms with this periodic ring of hydrogen.
Yeah.
What is the motivation to what is the motivation that you that you would like to resemble this periodic system with this non-periodic system? This I did not get.
Yeah, if we, so you understood perfectly well. So we really just want to, we couple only here at the end and try to mimic this periodic or quasi-periodic system with this small model. If we want to do this for a catalytic active center, then we would have somehow some, I think in the introductory example, it was iron, yeah, some iron atoms embedded in a lot of iron. And from this ion, there come all the other electrons and the interaction with the electron and the bias potential. So what we would ideally like to do is to just not simulate the whole periodic surface, but just take a small part of the surface, and due to the coupling, mimic all the effects the environment has. So it's basically kind of an embedding model. We take a subsystem and embed this via this coupling. And by appropriately choosing the parameters here, we hope to get an idea of, or to simulate the whole system, but now with the additional benefit that we can change the bias potential, which is something we could normally not do before.
I see. Okay.
I think there is a question.
Yes, there's a question from Margarita. Margarita, you can...
Yes, hello, I'm here.
Hello.
Hi, hello. It's thank you for a very interesting talk, and it's very inspiring in many ways. So I was wondering about the electrolytic, the electrolytes in the double layer. When you were calculating the Stern length, and you came to a value of 0.44 angstroms.
Yes, yeah. That is surprising, right? Because that is nothing.
Yeah, exactly.
Yes,
okay.
That is very well observed. Yeah, I mean, this is why I said before, there are so many approximations in this model. we should think more of it as a like one free adjustable parameter that somehow connects or does the right physics, but it has nothing to do with the real Stern length, right? So if there would be a full layer of water, that would be much larger than 0.44.
Yeah,
absolutely.
exactly.
Yeah,
okay.
Yeah.
Okay, so maybe it feels like the extra value that you need to add to something that has more physical meaning, and this field effect is consistent with that 0.44.
Can you say the first part again? Sorry.
Okay, so you have to consider the water that it's close to the electrodes, close to the field. So that gives you a length of that that is not yes, that one. And then you are adding that Stern value that you add, is just like making it a little bit longer to incorporate the field of the ions themselves.
Exactly, yeah. And I mean, you could treat this also a bit more difficult, because the offset here for the water, then we just used values that were parameterized for a solvent model without electrolyte. And you could, of course, argue there are like osmotic pressures and so that change the situation. So you could also think about changing this offset here again. And then maybe you would arrive at something that is a bit more realistic.
Okay. Okay, because that region, the offset that you said, that might change in the physical conditions of the solution, has also to do with the way that the polarization of the model is working. So we have been studying that for some time now, and different ways to include the polarization of the water model influence a lot the length of that surface. So that's something that it's very interesting to look, because the density in that region is very high, and the electric permittivity, of course, it's completely modified. Yeah. Thank you very much for your talk.
Yeah.
Thank you very much.
Thank you for the question. That's very good.
Yeah.
I will certainly look into your work then, if you're looking at the polarization. Thank you.
Thank you so much.
Okay.
Thanks for your talk.
Are there further comments, questions from the audience? My next question is actually related to your modeling of the solvent and the electrolyte. If I understand correctly, you use this Poisson-Boltzmann model, right?
Yes.
So there you assume some charge densities, or from where do you get the distribution? Yes, these rows.
These rows you get from the electronic structure calculation. So when you solve for the electronic structure of your molecule, you can calculate the rows right away. So you have the charge density of the electron cloud and the charge density of the nuclei, and you just add them, and then you have the charge density of your molecule or surface or whatever.
So let me see if I understand correctly. So in your molecular structure calculation, you simulate the electrodes, you simulate the molecules, and you put there the solvent and the electrolyte. All these.
No, sorry. So let's think about not about a surface for now, but just about like this molecule.
Okay.
And we solve its electronic structure in the gas phase, and we get this row from the electron cloud.
Okay. Fine.
And then we say, okay, we can now calculate the electrostatic potential from this. And if you modify the dielectric constant in some functional form, it will change a bit. And then we can do this iteratively to optimize also the electronic structure again. So that will of course be affected by the electrostatic potential. Right? The electronic structure will be affected by this external solvent response, basically. And this would be just a solvent model. And now we add the electrolyte ions in a separate term. And for the electrolyte ions, okay, we say this is they have a charge, sodium plus positive and chloride negative, and they have a concentration distribution. And this concentration distribution has a prefactor, so just the concentration in the whole solution. But then the position is modulated by the electric field. So the stronger the field, it more attracts or repels positive ions, for example, and rejects negative ions. And this is classic Boltzmann term. So of course it depends on the temperature here. And then you solve this whole thing iteratively. So changing this will change this, then this will change the ion distribution. Then so you have like a three-way nested loop, where you optimize for the electrostatic potential, and this goes back to both of these charge density distributions.
I see. And for the concentration of the ions, you use this Poisson-Boltzmann expression.
Yes, exactly. So that we just assume Boltzmann distribution. That's basically the idea that Gui and Chapman had, that you have this diffuse cloud here.
Now I understand. Now I understand. Okay, yeah. Okay, I see. Let's see. Could you imagine to make an MD simulation for this concentration? Would it give better results? Because you later showed these results with chlorium and sodium close to this electrode surface, where you did this MD simulations.
Yeah, so MD will always be better if you have a proper force field or whatever you're doing, but it's just too costly most of the time for what we want to do here. I mean, there's really nice work now where people do ab initio MD calculations, and they have nice ways to include also the bias potential on the electrode, so you do really the full electronic structure calculation with ab initio MD, but this is super costly. So it can be done. It's like, I also don't want to call it brute force, because there are so many intelligent ideas that make it possible with today's hardware. But yeah, this is a more direct way, but still very expensive.
I see. Okay. Yeah. Are there further comments, questions from the audience? If this is not the case, Christopher, thank you very much again. Very nice, very inspiring talk. Very good work. Yeah. And yeah. Bye-bye, everyone. See you next week.